It's my pleasure to introduce Damien Pous, who is a senior researcher from CNRS. Damien is a member of the LEAP laboratory in Lyon, where he's leading a team of experts in logic and semantics, working on improving our understanding of proofs and programs. Damien got his PhD from ENS Lyon in 2007. He did a postdoc at UPenn and then became a CNRS junior researcher in Grenoble and in Lyon. In 2016, he got an ERC grant, and 1 year after, he became a senior researcher. So during his PhD, Damien worked on concurrency theory. This inspired him to develop new algorithm and proof techniques to improve deductive verification and to apply them to concrete problems. He has worked on a number of topics, such as automata algorithms, clean algebra, co-inductions, and cyclic proofs. He also contributed to several work formalizations related to relational algebra, partial orders, graph theory, and categories. Today, we'll talk about medium-scale automation for proof assistance. So, Damien, I'm glad to have you here today.
Thank you. Thank you, Sandrine. Thanks to POPL for inviting me. Thanks to you for being there. I'm quite honored, impressed, delighted to be here in this beautiful room. And today, I'll just start a timer. I'm willing to talk about automation in proof assistance. And actually, a better title for my talk is this. I want to do better proofs using proof assistance and using some automation. So what does it mean to be a good proof? This is the first question. And the second one is why do we need proofs? And my claim is that we need proofs to convince people that something is true, to convince people about why something is true. Okay, so correctness is not the only thing. So a good proof should be correct, but more importantly, convincing. You can have proofs which are convincing but not correct. So that's not so nice. You can also have the converse, sadly. Another criterion is being concise, okay? Because it's easier to convince someone with a short proof than with a very long proof. However, there are constraints. Some problems are inherently complicated, and we know that there are statements whose smallest proof is arbitrarily long. Okay, so you cannot be always concise, but you should strive for conciseness as much as possible. And there is a balance here, right? If you want to be correct, you need to provide all details. If you want to be convincing, probably you'll need to elude some details which are too boring. Okay. First criterion is being reusable. You want your proof, certainly, to be reused by other people. And here I don't mean the statement of the theorem, I mean the proof itself. A nice proof often contains interesting ideas which you want to reuse somewhere else in other contexts. So proof should be reusable. First point on correctness. For quite some time, it was not that easy to have correct proofs. And it was rather subjective. Right? The proof is correct because I didn't find flaws, because I trust the authors and so on. Nowadays, with proof assistance, we can do better. It suffices to trust the proof assistant, which is quite nice, actually. There is still a notion of trust. I mean, the proof assistant could be flawed, your formalization could be flawed, but still, I think nowadays we can assume proofs are correct. And this is very nice because once a proof is correct, we can make it more convincing, more easily. Now, how to make, what is a convincing proof? A proof is convincing, your proof is convincing, if I can understand it. Or maybe I can explain it again. It's also convincing if I can use it and adapt it to other needs. Right? And these two criteria, they also work for programs. Proofs are programmed, remember. So a program is convincing if I can understand its code, if I can use it, if I can adapt it to other needs. There are possibly correct, yet very unconvincing proofs and programs in the nature. And let me discuss a few of them. One category is the write once, read never proof or program. This is a proof or a program which you've spent a lot of energy and maybe a lot of fun writing, but it's so complicated that no one will read it. Example. My first ray tracer. This is a very fun program, but the code is awful. It still works. I could get this picture, but I would not adapt it, right? Second example, your first submission maybe. Or maybe the appendix of your last paper. And unfortunately, many formal proofs are like that. Since we have correctness, once it compiles, we push on Git, and then we forget about it. And we cannot read it anymore. And this is not good, right? You need your proofs, even your formal proofs, to be readable, reusable, and so on. Another category of proofs which are not completely okay, but still wonderful, are the read-only proofs. Proofs which are there, you can use them, you can understand them, but you cannot reuse them, you cannot adapt them. Here is one. Here is a very convincing proof that you can put 8 queens on a board without them hitting each other. It's concise, it's convincing, but if you slightly change the statement, it's useless. Right? Another one is this small program to compute the inverse of square root. It's some code which is in the video game Quake 3, for those who know. And it only uses a few multiplications, and you get the square root with a fairly decent amount of decimals. So this is like magic. And it works. You can use it. It's sufficient for a video game, but you cannot use it in other contexts. Yet another one is this proof of irrationality of zeta of 3 by Aperi. He came up with this very strange formula and a bunch of other ones. And using this magic formula, you can prove irrationality of zeta of 3. But this formula came from an oracle. I mean, you don't know how to adapt it, how to make it work for zeta of 5, maybe, or something like that. And again, when we do some formula proofs, some of our proofs are like that. We use some complicated techniques. They happen to work. We don't know why. They just worked. We didn't think about it, and we left it in this way. And then the proof, is very fragile. You try to adapt it to something else, and it fails, and you don't know why. And this is not good. Still, there are cases where you can improve the situation. In those 3 examples, basically we had oracles. And here, for the first example, the oracle is certainly a SAT solver. So a better proof for this statement is the same proof together with the comment, I got the solution with the SAT solver, and here is the script I used. Because if you have this, then you can easily adapt the script and maybe hope for a proof of a slightly different statement. Here, I don't know what you can do. Here, maybe you can add Aperi's phone number next to the proof. Okay. So the challenge for me really is to make it easier to write convincing, concise, and robust formal proof. Concise because it makes it easier to be convincing and to be robust. If you want to maintain a proof, if you want to adapt a proof, it's better if it's concise. And robust because you want to experiment with your proof, move it a little bit, and it should still remain a proof. Okay. So outline of the talk, I'll do 2 case studies, one in relations and one with monads. And in both cases, the game is to find the right abstraction level and to design and use appropriate infrastructure to work with these abstractions. So for relations, it will be regular expressions, clean algebra. For monads, it will be monoidal categories and string diagrams. Okay, so let's start with relations. I want to prove this very small, very basic theorem, maybe it's just a lemma. If two relations are transitive, then so is their composition. First, I have to define transitive. So I could use a definition like for all x, y, z, related by R, there exists, by R and then, anyways, a relation definition with points. This is painful, I cannot even do it right now, I'm too stressed. But you can also say a binary relation T is transitive if TT is below T. T square is below T. Okay. Second step is to fix the statement. My statement is completely wrong. Did you see it? Yes. Okay. You need an assumption. And this one is sufficient. If S and R commute, then you're fine. And then you can write your proof. So this is a paper proof. I find it concise and convincing. Right? You swap S and R in the middle, and then you use transitivity of R and transitivity of S, and you're done. Now what I want to do is to have the same form of concision and convinceness in the proof assistant. So let's do it. Is it big enough for those in the... Yes? Okay. So here's the statement of my theorem, or lemma. Okay? And here is a first proof. What do? I want to swap S and R in the middle. Maybe I should display the goal here. I want to replace SR with RS. For this, I have an hypothesis, but I cannot use it right now. Right? There are parentheses which I should reorder in order to be able to do my rewrite. This is a bit painful, so I do it. I put parentheses right, then I rewrite. Okay, I get there, but now I want to replace R by R and SS by S. Again, I do have hypothesis for this, but I have to mess with parentheses before I can do it. I do it, and I'm done. This is a concise proof, but it's not satisfactory, right? You don't want to have those intermediate steps to deal with parentheses. Also, it's really not robust. Maybe if I set up a new notation to make my statement more concise. Okay, I want the square of a relation, and now I want to state everything with squares. This is the same, right? But now my proof breaks. I don't want this. I don't want a proof to behave like that, right? I want something which is robust with respect to this kind of change of notations. Okay. So let's do another one. Here's a second proof, a bit longer, a bit more explicit. I say, well, first thing, I want to replace SR with something. So let me make it appear explicitly with the transitivity step. And this, then I get two goals. One which is easy because it's just about parentheses, and I can solve it with some tactic. And the other one, which is the one where I can rewrite. Okay. Same thing for the other steps. I can message the goal explicitly to be under shape. I can use it. So here I want RR and SR, and SS. Again, array solves the goal. I could even have used my notation here. And then I can do my 2 rewrite steps, and I'm done. This is more robust, but this is less concise. And it's a bit painful to type those terms with parentheses. So what can I do? I can do a third proof with some more automation. Here I have access to a tactic mRewrite, which does perform rewriting modulo associativity, so that I don't have to care anymore. And I just do the 3 steps which were on the board before. And this proof I find concise, convincing, and robust. So this is the kind of proof I aim at. Okay. Let's do another one, slightly more complicated. Here's a small lemma, again, a bit bigger about relations, about reflexive transitive closure. And a proof below in Isabelle, which is correct, a bit long. You can still get some insights by reading the proof, but the statement is too simple. You don't want a formal proof to be that long. What else can you do? You can call the literature. There are theorems. In particular, there is this one. The equational theory, this is a bit, the equational theory of relations, restricted to regular expressions, is decidable by this characterization. 2 expressions are equal if and only if they denote the same language, are equal in the relational models. And deciding language equality is okay. There is an algorithm for it. So you can code this algorithm. And since you are in a proof assistant, you can even certify this algorithm and execute it inside the proof assistant to get proofs. This is called reflection. So using reflection, you can use your favorite decision procedure in order to solve your favorite problem in a certified way. So this proof, which we had before, nowadays, we can just, here it is, we can just prove it with a tactic. Ka, for linear algebra, solve this goal immediately by running an automata computation. This is concise. This is convincing if you believe the theorem. I mean, if you understand the theorem that says that you shouldn't care about such equations because they are decidable. And it's robust because now if I change something, I don't know, if I swap two things in my statement, the same proof works. I don't have to go into the proof to find where I had to use R and not S and rename all my hypotheses and so on. Okay. And you can do other examples like that, which I'll skip for now. Okay. Another example, if you want to study confluence or commutation of relations, of maybe rewriting relations, certainly you have encountered this lemma, Church-Rosser, which says that if 2 relations commute strongly, then their reflexive transitive closure also commute. You can state it algebraically in a very natural way. And when it comes to the proof, you need an intermediate lemma. You need to do the 2 stars one by one. And the two steps are proved by induction. Certainly you have seen these proofs many times. And again, I want these easy proofs to be really easy in a proof assistant. So what can I do here? This is my lemma. This is the theorem, actually, the first line. And then there is a lemma. I want to prove this lemma inside by induction on the star. Actually, the star which is on the left. So I start my induction. Up. Base case is trivial. This is just Ka. And inductive case, you have to use your hypothesis. You can do it modulo associativity. There. And then you conclude by Ka. Up. So you have the lemma. And now theorem out of the lemma will be the same, except that I do an induction on the right. Base case is again trivial. Now you have to use the lemma inside, and you're done. Okay, so this is good because it's again concise and rather convincing. You get not much more than the intuitions that were on the slide. And is it robust? And I claim it is. For instance, you may know this variant of the lemma. If you have a reflexive closure here and a transitive closure here, it still works. So can we adapt the previous proof? Yes, we can. So here I just add my, let's do the star first. I add the star here, and I think the proof just completely goes through. Because KA, the tactic, takes care of it. It's automatic. Now if I want to add sorry, this is not here, the reflexive closure here, it's a bit more complicated. The proof fails. It fails by saying, oh, look here, this is not a theorem. This is not a theorem because one, the empty word, is accepted here. No, the goal is not synced. But one is accepted here on the left, but not on the right. You see that there is an error here. So I should look at my proof and understand what failed. And in fact, what failed is that I should fix my intermediate lemma also for the proof to go through. And it still doesn't work because here I introduced some a case distinction which has to be there, but I can easily fix it. I don't explain you why, how, but you can easily fix it. And then you're done because the rest of the proof goes through. So here, the same proof doesn't work, but I can easily adapt the proof to make it work. This is what I call robust. Okay. So, was this convincing, concise, and robust? Concise, yes. Convincing, you have to accept that you can abstract away all details about regular expressions. But besides this is okay. And robustness, I think it's robust because the KA tactic solves a very well-defined problem. And there is a complete algorithm for it. So either it succeeds or it fails. And when it fails, you know why. And this is very important for robustness. Okay. For reusability, another important thing is abstraction. You need to state and prove your results in the most general form, right? And here we can use the strengthening of the previous theorem to do that. This is a theorem I've shown before. In fact, there is an algebraic version. Not only the equational theory of relations is decidable, but actually the equational theory of all linear algebras, which is an axiomatic system. And this theorem makes it possible to apply the previous techniques not only to binary relations, but actually to any linear algebra. And the proof which I've done before, they would scale without doing anything to an abstract context where now the statements would be about elements in a linear algebra. Let's see this. Actually, if here at the beginning of the section, instead of assuming that I have a type and a few relations, I assume I have a structure. Here it's a partially ordered monoid, and elements of it. The same proofs will just go through, all of them. Well, all of them except at this point where here you use KA, the clean algebra structure. So you need to have it, and this I say it in this way. Okay. So by moving to an algebraic framework, I can extend, this time not the usability of the proofs, but the usability of the statements. And here, it looked easy in the proof, so I just had to change the context of my proof. The hard part is improving the completeness here. The fact that if E and F are equal as expressions, then you get a proof in Ka. And this is a very nice proof by Kozan and Krob independently, which you have to formalize in ROC in order to use it. Okay. Regarding clean algebra, there are many extensions of clean algebra in the literature. Maybe the most important one being clean algebra with test, which you certainly know very well at POPL, which is an idea by Dexter Kozan. And here I'm in green there because what I did is to put this thing in ROC 10 years ago. Each time in those extensions, decidability is delicate, also completeness is delicate. Sometimes you have decidability but not completeness. But it's difficult, and so far it has not been implemented in ROC. I wish it were, when it is decidable and or complete. And to see why this could be useful, consider this example, which I had presented a long time ago at POPL. You want to show the equivalence of these two flowchart schemes. And there is a proof in this nice book by Mana, where you move from one to another progressively with some intuitive explanation about why you keep the same semantics. And so they managed to prove the equivalence of those two flowcharts. And 30 years later, Dexter Kozan and Allegra Angus redid this proof using the algebraic technology of CAT. And they managed to write a much more formal proof, much less hand-waving, using 6 pages of CAT computations. This is a nice exercise, but it's really a write-only exercise. If you open the paper, I mean, you can read, it's correct in the end, but it's much easier to write than to read. And what I did is to formalize this algebraic proof in ROC, and here is the proof. It's only three screen long. It's also write-only. You don't really want to read this. But at many places, I use a high-level tactic, CAT or HCAT, to solve, to go from one step to another when it is possible to do it automatically. And without this tactic, I would not have been able to formalize Dexter's proof. Because there are places where you save pages somehow. Okay, so this was to show that this technology, which I illustrated on very small examples, is also useful on larger examples. And it's important to have good abstractions, good techniques to deal with the most basic things in order to be able to scale and do more complicated things afterwards. Okay, that was about relations. Now let's move to the second case study, which is about monads. You certainly know monads at POPL. You know that they are useful for effects, algebraic effects. You know some of them. There is a state monad, exception monad, delay monad, and so on. There are many other ones. Lists, multisets. And here in this talk, I'll consider this joke from category theory people. A monad is just a monoid in the monoidal category of and of functors. It was a joke, because it's abstraction for abstraction, and who cares about abstraction? But I'll take it seriously now, because indeed, this is the right setting to talk about generic results on monads. And for this, I'll need to explain you a bit about monoidal categories. Not too much, be very short. First, categories. You have objects, uppercase letters, morphisms, lowercase letters, composition, which I'll write with a semicolon using the more natural way of thinking, and identity. Should be okay. Monoidal categories, you have the tensor product. Tensor product is somehow the ability to put two morphisms side by side. The formula is not so nice, but it's quite simple. You just have take two morphisms, f and f prime, You put them side by side. There are other details about monoidal categories, associators, unitors. For now, we don't care. We do the strict thing. Then comes the painful thing, laws. There are laws in monoidal categories. In fact, there is mostly one law, which is bifunctoriality, which is this formula here, which as a consequence has this other law, exchange. And this is painful. I and j, they look ordered, but they are not, because you see that j here comes first. And here I and j are far away, while here they are close. And it's really hard in terms there to see what is close, what is far away, and so on. In fact, it's a bit like this 15 game. Terms in monoidal categories are like that. You have very basic moves to transform them, but it's really hard to know when you can put things together. Fortunately, people have invented string diagrams, which is the good abstraction for monoidal categories. So here is a string diagram, and to give more intuitions, I will use a small tool. So here I'm in a context where I have three morphisms, F, G, and H, of those types. And maybe I can display F as a string diagram. So this is just a box with two inputs, A and B. This is written here in the type, and one output, B. So inputs are upstairs, outputs are downstairs. I can depict G. This is just a box with one input, one output. I can depict H, a box with two inputs, two outputs, and somehow it swaps the two strings. Then I can do compositions. I can compose F with G. This is vertical composition. Semicolon is vertical composition. Okay. So here you should look at this term, which I'm writing, and see how it relates to the picture. I can compose them horizontally with a tensor product, which is written with a small dot. Okay. So here I get a box with three inputs and two outputs. And so once I know I can do this, I can do combinations, right? Since I end up with B and C here, I can plug in G again. Not G. H, thank you. Okay. And here maybe I want to plug G again on this, in this place, but G alone is not enough. Because here I must plug a box which takes some CB, not just B. And in order to do this, I can use the identity here. And the identity, I can write it either as ID or as the object. It depends what you want to emphasize. Okay? So these are string diagrams. Why are they useful? They are nice, but why are they useful? They are useful because they make it possible to abstract away those painful laws which we were seeing before. So here is just I compose tensor J. Okay, so two small boxes, and the exchange law from my slide before this one, the second one, actually is the fact that Ij, I can see it in other ways. I can see it in this way. This is giving priority to I. I first, then J. Another way to depict it, say I can go up and J can go down. Okay, and I can see this diagram as I with the identity composed with J. Of course, I can also do the converse, right? I can put J first. And all this law is saying, the second one, is this, that you can slightly slide the morphisms in your picture. Similarly, for exchange, for bifactoriality. So here, this is written as f prime composed with gg prime, but I can decide to write it as a single horizontal composition of two vertical composites. And this is really bifactoriality. But I have other choices. Maybe I can put f here in the middle. So here, this is a composition of vertical composition of three things, and many other choices. So this is why string diagrams are useful. In fact, there is this completeness theorem saying that two expressions in monoidal categories are equivalent if and only if they denote the same string diagram. So this theorem really says that string diagrams is a good abstraction for working in monoidal categories. This is how you want to think, and this is also how you want to implement things in a proof assistant. You want to reason automatically about these equations. In fact, when you have two expressions like that, you have a way to decide that they are equal or not, an algorithmic way, and this should be implemented in a proof assistant. You don't want to solve this by hand in the proof assistant. Okay. Now let's go back to monads. Monads, which I've told you, are just monoids. So I should explain you what is a monoid. A monoid is an object with two morphisms, mu and eta. Mu is the multiplication, eta is the unit. And now if you think concrete a little bit, if you go back to monads in sets, you should think of objects as functors, tensor as functor composition, and arrows as natural transformations. And maybe the monad M is a multiset monad. Multiplication here is take a multiset of multisets and flatten it into a multiset, and so on. But here it's abstract. You don't really need those intuitions. You just have these morphisms. Now, I've told you we should use string diagrams. What are the string diagrams for those two morphisms? Well, we can depict them in this way. A box with two inputs and one output, and a box with 0 input and 1 output. This morphism should satisfy a few laws. I mean, it's a monoid, it should be associative. And the standard laws are those ones. Painful to read. Not too long, but... You can draw diagrams for them. Slightly better. Maybe here this is really the diagram for associativity. This is where you understand that this is associativity. You have two ways of going from M3 to M, and those two ways should be equal. But what's the good way of thinking of this is the string diagrammatic way. Here are the diagrams. That's much nicer. So here, you collapse two things into one on the left, then on the right, and here same thing, first on the right, then on the left. This is really associativity. Here I've just written the diagrams for the two terms, and same thing on the right. Okay. Now comes the theorem. I want to compose monads. You certainly want to compose monads. You want to combine effects. You want non-determinism with state, non-determinism with exceptions, with probabilities, and so on. And for this, if you want to stick to algebraic effects, you need to compose monads. In my setting, this is just composing monoids. And you certainly know that there are conditions, very much like in the first example of the talk. You need distributive laws. Okay. A distributive law is just a morphism from NM to MN, which you can depict using this small box, which allows you to cross strings. And if you are given such a box, you can easily construct a multiplication, say, on Mn. This is this diagram. This is a diagram from Mn square to Mn, which I obtained by swapping the two people in the middle and then multiplying on both sides. If you really insist, I can give you a term for it. But I don't care about the term, in fact. Now, distributive law of monads, they should satisfy some law, some coherence law. So the exchange should play well with multiplication and unit. Here are the laws. I mean, two of them, I forgot the unit, and I'll do in the rest of the talk. You can draw diagrams again, which are not so illuminating. Or you can draw the string diagrams, and there you start understanding. What you need is that the fork, the multiplication, should be able to go under the cross, the exchange here, and go there. On one side, and also on the other side with the other fork. Okay, so let's get back to the theorem. I want to prove it, so I define my new multiplication, this strange mu, here, and I need to show associativity among the other things. Here is a diagrammatic proof. It's correct, it's awful. Still, we can get some grasp on it. Let's abstract a little bit. I remove irrelevant details. Here, if you look carefully, you'll see that you use associativity of the two monads, here and there. Those are squares. And there are also two pentagons here, where you use the interaction between the exchange law, the distributive law, and the monads. And all other squares and triangles, they are just exchanged by functoriality, which in the special case of monad is naturality of concrete monads. So all those, I think there are 13 steps here. There are painful steps which you don't really want to see, in fact. What you want to do is a string diagrammatic proof, and it will look like that. I will not discuss it right now because actually what I want is a string diagrammatic proof in rock. And this is what I'll do now. So where is it? Here. Here's the statement. I have a monoidal category, two objects which are monoids. So here is the multiplication of my monoid, its associativity. Here is multiplication of the other monoid, associativity. Then there is the distributive law, X, and its two coherent axioms. I construct the composite multiplication here. So here I need the term. This is the term that was on my slide up here. This term. And I proceed to proving associativity of this composite multiplication. What can I do? I'll just copy-paste the goal into this wonderful tool, which is there, blank. I copy-paste. And here, what do I get? I get the four equations, the four hypotheses, so associativity of the two monads and coherence laws, and my current goal. I should show the equality between those two string diagrams. Where here, the orange boxes, they are the composite multiplication. I can open those boxes. Yep. And now I can start working. What do I want to do? Given the laws which I have here, maybe this fork is willing to go down. So I can select this pattern. It matches one of my hypotheses, and thus I can replace it with the right-hand side. Same thing on the right-hand side. Okay, I see a pattern, it matches one of my hypotheses, I rewrite using it. I'm not yet done because you see that the monads are not in the same directions, the turquoise and violet monads. So I should still reorder those. And same thing, let's do it nice on the right. Great, I'm done, I've obtained the same diagrams. But for now, this is just some OCaml code with my mouse on the computer and so on. I want something formal. And now there is a button, which is a capital E, I think, which tells me rock script copied to clipboard, which means I can go back to my rock proof and copy it. Here is the proof. So it's short. It's not extremely short, but it's short, it's concise. What is happening? Basically, the proof is just 4 rewriting steps, right? They are there, the 4 of them. Yes, you see. Each time, I do a transitivity step where I make it explicit that there is some match. Here, this is the left-hand side of NX. So I do a transitivity step to make this subterm explicit. Then I use an automation tactic to solve the goal. Okay, the 2 terms, the previous one and the one where the match is explicit, they are equal, they have the same string diagram. I can solve this automatically. And then I can do the rewrite as expected. And I continue. I want to do the second rewriting step, same strategy. I make it explicit that there is a pattern. To make this explicit, I use automatically, I use the MCAT tactic, and then I rewrite, and so on. And in the end, I get 2 expressions which have the same diagram, so I can prove them equal using MCAT, and I'm done. Okay. So here's the proof in rock. Is it convincing? I hope so. Well, if you understand string diagrams, it should be convincing. Is it concise? It's concise. It could be more concise. For instance, I could hope to replace those transitivity rewrite steps by a single call to an M-rewrite tactic, which doesn't exist, which is rewriting modulo string diagrams somehow. This is feasible. I'm willing to code it. But before coding it, is this proof better than the previous one? This, I don't know. It's more concise, but if you just read it, you get less information. So maybe, in fact, the previous proof is slightly better. For me, both of them are robust. If you slightly change the statement, which you cannot really in this example, but both of them would be okay, because this one, you would expect M-rewrite to take care of the work, and this one, you could hope to modify manually the terms. Okay. To show you that it's convincing, I could do 3 monads. I won't because I don't have time, but it's a very nice exercise to do. And you'll discover, doing the exercise, that it's not obvious which laws you need. Certainly, you need 3 distributive laws, but in fact, you need a bit more, and this you discover when you do the exercise. And this is nice. Under the hood, maybe you have noticed that there was these strange symbols, prime here on equiv, and a double semicolon. And these are not typos. If I go back here, You see them here, prime, 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 double semicolon, double semicolon, double semicolon, blah, 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 blah. In fact, those are notations which make it possible to elude all questions about associators and unitors, which you have to take care about, which are painful to do. In fact, even in this ugly proof, they are not there. This is a proof in strict monoidal categories. But strict monoidal categories, you cannot formalize them, really. You will end up having equalities anyway, so in the end, you will have the same amount of work to do than to formalize arbitrary monoidal categories. And here, it really works because I do have this setup to infer automatically what are called MacLane coherence morphisms. So to show you here I cannot write a single semicolon because it does not type check. Because here you have two tensor expressions in the middle which are not associated in the same way. So for it to work here, in the middle, you need to add something, associators. And those are really painful to write explicitly, so you want to infer them automatically. And I do here. I do using those notations, using some powerful mechanisms. And this you can do safely because there is a nice theorem, MacLane's coherence theorem, which says that any two MacLane morphisms with the same sources and targets are equal. So you can infer them automatically because you don't care about which one is chosen. And this is really crucial. Okay. Now, to sum up on the two case studies, what made it possible? First of all, nice theories and abstractions. So clean algebra on one side, string diagrams on the other side. In both cases, those are quite old abstractions. Second, you need decision procedures. And to go to proof assistance, you need certified decision procedures. And here, what I use in a very strong way is reflection. The ability to compute within the proof assistant in a certified way in order to get proof. I use it at many times, not only for the three tactics which we have seen, but also for this MacLane morphism inference. Here I do this by reflection again. And lastly, you need powerful notation systems. It wouldn't work without those notation setup. The tool is in strict categories. I don't care in the tool, when I program in OCaml, about associators and units. The ROC is with associators. And I can communicate between the tool and ROC because I managed to set up a nice notation system. Otherwise, I would not be able to communicate. So this is really crucial. There are other theories which can be automated, which are automated. I list a few of them here. And all of them help us writing better proofs, I think. And in this list, all of them are rather robust. And they are robust because in each case you have clear specifications and you have complete algorithms. I insist on complete algorithms because if you have a semi-decision procedure for something, it cannot be robust. It will work in one case, you will try to adapt it to some other case, it will fail or not terminate, and you won't know why. It's not problematic that it fails, but it's problematic that you don't know why it fails. And this is really important. This is what makes things robust. I've also not discussed other important automation tools. There is generalized rewriting, where there is quite some work in various communities. And even more importantly for me in this work, even though I didn't show it, there is a support for hierarchies. You need to set up hierarchies of structures and to set up concise notations. This I explained. And for this, you have to do a lot of work. And for now, this is rather ad hoc work. And here, I think there is a big room for research within POPL, taking inspiration from programming languages to provide a structured way to do notations, to do structure inference, and so on. And I'll stop here.
Do we have questions in the audience?
Hi, thanks for the very nice talk. I was wondering how widely applicable the whole rewriting modulo sum matching would be. Have the same very similar pain points with the equational theory or substitution calculus. You also want to apply lemmas up to that equational theory. And it's also extremely painful, and I'm really, really wanting whatever mrewrite is doing.
Should stay here. I would say the approach is quite generic. At first, you need a decision tactic for the equivalence. And this has to be certified. Then you need something to detect matches. Something which is able to, given a term, see if there is a way to write another term with an explicit match. And this, of course, depends on the theory. If you just do associativity and commutativity of some symbols, there are algorithms. If you do string diagrams, there is an algorithm. If you do linear algebra like I did in the beginning, there is no algorithm. You cannot rewrite, you cannot find a match modulo linear algebra axioms. There you could do heuristics, but then you get the problem that it won't be as robust as you might hope. But the overall approach is quite generic. Then it depends on each theory, whether you can find a matching algorithm.
Thank you. Okay. Thank you for the talk. So you had this nice tool that you wrote in OCaml to like fiddle around with the string diagrams, and then at the end you generated a rock proof. Did you ever think about integrating that? So I think in the competitor, so in Lean, they have like all kinds of fancy ways where you can display proof states in some nice way. And also in Rock there's Electron. Did you ever look into that?
So to integrate the thing, the way I proceeded makes it partly easy to integrate. The standalone tool is really standalone. To communicate with it, all you need is to be able to write and read in a text syntax. So then you have to go to your proof assistant and to set up a framework to work nicely at this abstraction level. So for instance, you need the MCAT tactic. So if you can redo the MCAT tactic in another proof assistant, you're on good track. Then you also need to do the notation system. You need to be able to infer McLean morphisms nicely. If you can do this, then you're fine and you can swap Rock for another proof assistant.
Yeah, but that was not entirely my question. My question was, did you ever think about integrating this tool in the proof assistant so that while executing this proof script, you would actually see the string diagrams on the right in your proof state, and you could actually change the string diagrams there and would immediately insert like the corresponding tactics?
You could. That would be really easy, except I don't know how to do it because you have to go into the internals of the proof assistant. And not only this, but also the internals of the interaction of the proof assistant with the text editor, which I don't really know how to do. This is why I delegate to me doing some copy-paste. But right now, you are almost there, right? If you're in this proof, I didn't cheat. Here, maybe you can do some manual steps here. Okay, imagine the first steps, I did them manually. I can, at any point, copy-paste the goal, go to the tool, and now what I see is the current state of the goal. And I can resume from there. So, and it's really important, indeed, that there is a small step correspondence between what I can do in the proof assistant and what I can do in the external tool.
So that already works by that you can just copy-paste this proof state. So that
yeah.
Thanks.
I had a question regarding M rewrite again.
Yeah.
What happens if you have multiple matches, multiple way to rewrite the equation you want to rewrite?
Yeah. Maybe this is why I don't want to, I didn't implement it yet, or maybe I won't implement it. Here, even in the tool, I didn't do it. Here, I have this idea of selecting a match and finding the hypothesis that match, which is automatic. It would make sense to do this, right? Click on this hypothesis and have displayed in the main term here all matches, and then select one. This is feasible here in the tool, and this starts being painful in the proof assistant, because then you need a way to designate or to enumerate all potential solutions and say, well, I want the fourth one. But if you start using numbers, then you are not robust anymore.
Yes, hi. Thank you for the talk. It was great. So I have a follow-up question on the previous question. Now here in the tool, you're selecting the term that you want to rewrite.
Yeah.
But the tactic that you produce is just a rewrite. How does that select what term you want to rewrite on the rock side?
Here, what I do, let's say, where am I? Maybe suppose I want to, I do this thing. Okay. Here I select a box, and when I select a box, I can extract with E a term for this graph where this box is highlighted. Here you see this term, and there is a box here which corresponds to this subterm. So this is a computation which is easy to do on the diagram. And now this term, which I can easily extract, is the one which is given back here in the proof as a transitivity step. What happens? Here, I don't know if it is this one, maybe it is. This term here is the one I could compute just by looking at this picture with an isolated box. And this is how it works. If I want to do a rewrite step in the tool, I translate it back to a transitivity step through the explicit term, then a rewrite.
Does your transitivity then ensure that there is only one match?
There can only be one, because the match is given with these small boxes. And actually, so you might decide to put two of them. And this is what I do in the displayed proof here. This is a slightly reworked proof here, which is displayed. This is not produced by the tool. This is adapted. Here, the first one is produced by the tool. The second one, I realize that I can do two rewrite steps in parallel. So instead of doing it like before, I make it obvious that there are two matches, and then I can do the two rewrites. So there is a lot of flexibility here. Basically, you can do whatever you want. Yeah.
So you've explained how there's various principles that help humans create convincing proofs. Do these principles also apply for LLMs creating the proof scripts?
I don't know. Maybe we should ask to ChatGPT.
Okay, just let me remind you that the talk is mirrored in the other room, so we have another question, maybe from one other room. You can also ask questions from Discord, and here is one I'm going to read. In your examples, medium-scale automation builds on nice abstractions for the problem domain that come from decades of research. How would you try to automate more in progress theory?
That's a fair question. I mean, I think we should start from the basic and automate more and more until the point where we understand. There is this challenge, for instance. Right now, when I did this work, it's still quite ad hoc. I use some knowledge, some tricks in the proof assistant in order to be able to implement notations, to implement structure inference, and so on. And this is still ad hoc. So, and even on small examples or long-standing examples, say, like that, it's not that easy to make it right. So I think first we need tools, and this is where I call for the PL community, tools to be able to do this in a more systematic way, even on simple case studies like the ones I've discussed. And I think only then we can hope to automate and to provide good abstractions for more recent, or more complicated often, theories.
Maybe a last question?
Hello. So
showed us this nice proof where you have 4 rewriting steps that the user has to find by hand. But if I want more automation, is there hope to automate the whole thing using maybe equality saturation or something like that?
You could imagine, yeah, you could imagine to have a kind of congruence tactic modulo string diagrams. I don't know if theoretically this has been studied, if this is really decidable, but maybe some fragments of it are. Here, also, you see that when you write it in this way, you can be more aggressive. Actually, the proof, if you generalize to many monads, you always have to let those forks go down and then reassociate. This, once you have an M-rewrite tactic, you could imagine to say, okay, rewrite as much as possible modulo the theory, the exchange of monads and distributive laws, get to a normal form, then do associativity, and conclude. This is feasible. In this example, it won't work, because if you want to compose, say, 3 monads, you need 1 more hypothesis, which is not easy to orient. So it wouldn't work by just normal forms, but still you would get to normal forms where you just have only this law to apply, so that's already some progress. And then in general, can you do equality saturation and so on? Possibly, that would be super nice to be studied.
So one of the key ingredients you said you had was that you're using reflection. You said reflection is necessary for this to work. Why is reflection better than creating proof terms?
Because proof terms would be huge, if ever you can write them explicitly.
Maybe they can be in memory, right?
Sorry?
You can have them in memory and check them in memory. It's still going to be faster than checking the entire decision procedure.
Let me go back to an example quite at the beginning. Here I produce proofs in Ka. Ka is an axiomatic system, so a proof is just a tree. It would make sense to, okay, have an oracle produce the explicit proof and type check it. Problem is, this proof, you don't really know how to produce it effectively. The theorem is constructive, so there is an algorithm, but it would produce a proof which is huge, but even more than huge. In fact, here it's much better to not produce the proof, to just run the algorithm that checks the equivalence of the 2 expressions, and know that when the algorithm says yes, indeed there exists a proof. The problem is p-space complete. We do small instances, so it's not a problem of being p-space, but the computation takes some time, it's okay. But the proof, the Ka proof it would produce would be enormous, and you would not be able even to just store it, I would say.
Thanks.
Okay, I think we should stop here, so in order to get to the coffee break. So let's thank our speaker again.